In this lecture, I'm going to be talking about the Big Bang. And before I do that, I'm going to give the sort of standard little disclaimer. What I'm talking about here is considered the scientifically accurate view of the origin of the universe. However, this should not be thought to be a criticism or conflict with anybody's particular beliefs. You can say whatever you want to outside of this class, that's fine with me. I am going to try to persuade you in this lecture that the Big Bang Theory is accurate. And yes, there's a hole or two that people sometimes might ask philosophically. And I'll mention those. But I'm going to try to give you the evidence that is why scientists think this is correct. There is really no other scientifically accepted concept for the origin of the universe other than the Big Bang. And so I really want you to understand why it is that scientists think this is accurate. Now, the basic idea of the Big Bang sort of comes from the expansion of the universe. If you think about the universe expanding, well, in the past it was smaller, and if you keep going back far enough, at some point in the past it must have been infinitely small. And in fact, it would have been very, very hot, very, very dense. And when we're talking about this, don't just think of all of the matter, all of the stuff in the universe. Think about space itself, time itself. Now, it's really hard to imagine universe without space, without time, but this is the concept. Space and time itself began with the Big Bang, and it would have been infinitely small. Where did this stuff come from in the first place? We don't know. Really, that's not an answerable question. What was around it? If it was this small point, how can you think of what was around it? We can't answer that. You can't really say there was anything around it. There was no around. What was there before this? We can't answer that. There is no before if there is no time. So the language itself breaks down when we're talking about the Big Bang. You just have to say, okay, this is how it started, and you can't really say before that or around that or anything like that. You can only talk about after the Big Bang, because there is no before, there is no around. There's no space or time prior to the Big Bang. And something happened that caused the universe to start expanding. Who knows what that is? People like to joke the Big Bang was neither big nor a bang. There would have been no sound. It's not really an explosion exactly. It just starts expanding. So this is the concept that the universe began as a single point with infinite density, and it suddenly began to expand out rapidly and dramatically. That's what scientists mean when they say the Big Bang. When we say that it is a theory, you should not think that there is uncertainty in this. This is the idea that we have for the origin of the universe. This is it. This is as certain as the theory of gravity. This is not supposed to imply any uncertainty on scientists' part. This is the only concept that we've got. We use the word theory because law doesn't really work here, but this is the concept, that the universe began as a single point with infinite density, and suddenly it began to expand outward rapidly and dramatically. That's what the Big Bang is. So how do we know? Well, the theory makes certain predictions. And these are predictions about things that we can observe today. We can't go back in time and see the Big Bang, but there are things that are effects of the Big Bang that we should be able to observe today. And if those predictions are in fact what we observe, then that provides evidence in favor of the theory. So just for example, if the universe began in a Big Bang, then the universe must be expanding. And in fact, the universe is expanding, so this supports the theory. So this prediction is actually sort of a backwards prediction. We had the observation first in this case and came up with the theory to explain the observation. But nonetheless, that does provide support for the theory. But it's not enough by itself because we did sort of come up with the theory to explain the observation. However, there are other predictions that are made that really do support the theory. And the strongest one is something called the cosmic microwave background radiation, or CMBR. Basically, when we talk about the CMBR, we think about the light from the Big Bang. If you could imagine seeing the light from the Big Bang itself, first of all, it would be everywhere in the sky, because the Big Bang happened everywhere in the universe at the same time. It covered the entirety of what space was at that time, and it's just gotten bigger since then. So the light from the Big Bang would be everywhere. Because the universe was hot and dense at the time of the Big Bang, the spectrum of that light would have been a black body. Remember that black body spectra that we studied back at the beginning of the semester are what you get from hot, dense objects. Well, the universe itself was a hot, dense object then. And you can do calculations based on what we think the age of the universe is to say that the peak wavelength of that black body spectrum would be microwaves. So the question is, do we see this? And the answer is yes. This was discovered by two guys named Penzias and Wilson. It's sort of a funny story. This is one of my favorite little stories in the history of astronomy. One of these two guys was working at Bell Telephone Labs, and he was working on satellite dishes. This is what was eventually going to give rise to cell phones, basically. And so he's working on radio receivers or microwave receivers. And he found that there was always this source of noise in his receivers. He had these receivers up on the roof of his building, and there was always this sort of background buzz in everything. It's not something you could hear, but it would show up in the data, and he couldn't get rid of it. And he was thinking, well, maybe there's a problem with the equipment. Well, he checks out everything he can possibly test about the equipment, and it's not the equipment. He says maybe it's because of where the thing is aiming. Well, they try aiming it in all different directions, it's still there. They think maybe it's spy satellites, and they try to research everything they can about spy satellites. It's not spy satellites. They think about radio stations, airplanes, nothing like that. They even think maybe it's pigeon poop. There's pigeons out there, maybe they're pooping on the dish, maybe that causes some interference. So they go up and they clean the pigeon poop off the dish. It's still there. So they don't know what's causing it. Well, one day he's talking to his friend, who is an astronomer at Princeton, and tells him about this whole story. Just sort of, this is what's going on at work with me right now. And his friend says, well, that's interesting. So it's everywhere in the sky, and it's got this peak in microwaves. Well, that kind of sounds a lot like what astronomers are talking about. What we would like to see is the background light from the Big Bang. And they research it further and study it in more detail, and eventually they are able to confirm that this is exactly what it is. This is the light from the Big Bang. And really, I mean, if you could turn your TV on to a station or to a place where it was just static, some of that static would be the cosmic microwave background radiation. It is detectable on any radio or TV or cell phone or anything like that. If you can find a place where you just get static, some of that is this radiation. And it matches the theoretical predictions of the details perfectly. And just show you this one thing. Now, this is something that came out in the 1990s. I was in college at the time. Now, you look at this and you're like, okay, black body spectrum, woohoo. Now, at that point, they hadn't really tested the cosmic microwave background against the best models yet, because you really need to go into space to get the best detail on this. The Earth's atmosphere and the radio signals that we have from Earth interfere with it. So if you really want to get good data, you go into space. So by the 90s, we had gone into space and we were making measurements. And I was at Trinity at the time, and doing astronomy research with my professor, and he comes in one day and says, Laura, you've got to look at these results that just came out in the astronomy journals, and it's about the cosmic microwave background radiation. And then he shows me basically this graph. And I was like, yeah, I know that's what it's supposed to look like, so what? And he says, no, that's the data. The points on this are the data. The line is the theoretical prediction that the theory predicts it should look like. The points are the actual data. They fit perfectly. You're never going to find a more perfect match between theory and observations than this. I mean, you get worse data than this when you do a lab. This is beautiful. This is incredibly perfect. This matches the prediction of the theory about as perfectly as you can get. This is very, very, very strong evidence for the Big Bang. There is one more line of evidence, if that's not enough for you, although for astronomers, that would be enough. That's a lot right there. But there is one more, which is called element abundances. Basically, if you think about the universe right after the Big Bang, it's very hot and dense. And basically what you have is a bunch of protons flying around. Well, if you have protons in a hot, dense place, like, say, the interior of a star, what happens to the protons? They start fusing, just like in the cores of stars. Except that in this case, it would have been in the universe as a whole, fusion would have been occurring. And we have been fusing hydrogen into helium, a little bit of lithium. But when the universe expands to a certain point, it has cooled off and become less dense, and so the fusion stops. Well, we can calculate exactly how much helium and lithium there would be as a result of this fusion, because we know at what point the fusion would have stopped. We know what conditions you've got to have in order for there to be fusion, and you can see how much helium and lithium would have fused in the time that you had for the fusion to take place. So the theory predicts the exact amounts. Well, we look at the oldest galaxies and measure their composition using spectra and see how much helium and lithium is there. We look at the old ones because in the really old ones, stars haven't had time to fuse hydrogen into helium and lithium themselves, and so we wouldn't have any contamination from what might have happened in stars. Well, if you look at the oldest galaxies, this matches perfectly. The amount of helium and lithium that we see matches the prediction exactly. So this is another strong piece of evidence. Basically, all of the predictions that the theory makes for what we should observe are things that we really do, in fact, observe. So this is why we think that the Big Bang is the best theory for the origin of the universe. Any other theory would have to explain those same observations equally well. If you've got another theory for the origin of the universe, you need to be able to explain the cosmic microwave background radiation. You need to be able to explain the element abundances, and you need to be able to explain the expansion of the universe. All of these things have to be explained in any theory of the origin of the universe because we know that those things are the case.